Hello, I'm Dave Brown for Tel-A-Train. Today we continue our study of centrifugal pumps with Part 2. Part 2 will be a bit more technical than Part 1, so if you don't get it the first time, watch it over again until you do understand. All right, to start out with, let's define a word or two. First, there's work. Work is a force applied for a distance. So when we sling the bucket or turn an impeller to cause fluid to flow, we are doing work. All right, now for a new definition for a common word. The word is head. When dealing with pumps, we normally use the term head when referring to pressure. This head is usually expressed in feet of water. We may also find pounds per square inch or PSI being used as well. The two methods of expressing pressure with centrifugal pumps are easily interchangeable. A head of 2.31 feet of water will exert a pressure of 1 pound per square inch. As you see here, this means that if we have a pipe 2.31 feet high full of water, a gauge at the bottom will read 1 pound per square inch. Or if we have a pipe 23.1 feet high full of water, the gauge will read 10 psi. Therefore, if our pressure is in psi and we wish to convert it to feet of water, we simply multiply by 2.31. On the other hand, if we start with feet of water and we wish our answer in psi, just divide by 2.31. Total head in a system is made up of three separate factors: static head, pressure head, and friction head. Friction head is in turn composed of three parts: friction in the pipe, entrance head, and exit head. To calculate the total head, we add up all the heads on the discharge side of the pump and then subtract from them all the heads on the suction side. Okay, first of all, let's look at static head. Static head is the height that a liquid is raised to. Here we have a simple system where the suction is 5 feet above the pump and the discharge is 10 feet above the pump. The static head on the discharge side is then a positive 10 feet. On the suction, it's a positive 5 feet. So 10 minus 5 equals 5 feet total static head. Okay, now what about the static head on a system like this, where our suction is 5 feet below our pump? Now the suction static is a minus 5 feet. So when we subtract a minus 5, it becomes a plus 5. So now we have a total static pressure of 15 feet. In case you get mixed up on the signs, just remember, if the suction liquid level is above the pump, it will flow into the pump by itself, so it's subtracted from the work the pump has to do. If it's below the pump level, the pump will have to do the work to lift it, and therefore it increases the total static head. Okay, now for pressure head. Pressure head has to do with closed tanks. On the system we were just talking about, we were pumping out of and into an open tank so that the water was at atmospheric pressure on both inlet and outlet. Right here, I guess, I'd better explain atmospheric pressure. This is the pressure caused by the air which is piled up on the Earth's surface. We don't normally think of it this way, but a block of air, say a cubic foot in size, actually has a weight, although it's not very much. If you took several thousand of these blocks of air and stacked them one on top of the other, you would have a situation much like we have in the atmosphere, and a considerable pressure is developed. At sea level, and at standard conditions, this pressure is 14.7 psi. And at 2.31 feet per psi, this converts to approximately 34 feet of water. This pressure is called atmospheric pressure. As you can see, this gauge is reading 0, but we just got through saying it had 14.7 psi pressure on it caused by the air that's piled on the Earth's surface. It reads 0 because the pressure is on the outside as well as the inside of the gauge. Most calculations use what we call gauge pressure, which is the additional pressure beyond atmospheric pressure that a normal gauge would read either at feet of water or psi. There's another term which is sometimes used, and that is absolute pressure. Absolute pressure is gauge pressure plus the 14.7 psi atmospheric pressure. Okay, back to pressure head. Now let's say we have a system like this, where we're discharging into a closed tank, and we want to develop 100 psi, which we will read on the gauge right here. Since the inlet and discharge are at the same level as the pump, there is no static head involved. And for the moment, let's disregard the other losses and consider only the pressure head. Since the suction is open to atmosphere, it has a 0 gauge pressure. The discharge reads 100 psi on the gauge, so the pump will have to develop 100 psi. If the discharge pressure we wanted to develop had been 114.7 psi absolute, the pump would have still only had to develop 100 psi, since 114.7 psi-A equals 100 psi-G. Suppose we have a system like this, where the suction side here is not open to the atmosphere and we're reading in psi absolute. The discharge is in psi gauge. Okay, we'll have to convert them both to either gauge pressure or to absolute pressure in order to calculate total head. Here's how it would go. Suction pressure head equals 64.7 psi-A, pounds per square inch absolute. 64.7 minus 14.7 equals 50 pounds per square inch gauge. The pressure is positive, so we put a plus sign in front of it. Now we have 100 psi-G discharge pressure head, so our total pressure head is once again discharge minus suction, or 100 minus a plus 50 equals 50 psi-G. For ease in the rest of our calculations, we convert this to feet of water by simply multiplying by 2.31, which gives us 115.5 feet. All right, now let's look at the rest of the losses in the system. First, there are friction losses. These are caused by the fluid rubbing on the pipe and valves. The amount of the losses can be found in tables in most hydraulic handbooks. Cameron Hydraulic Data Book is one of the more widely used ones. The way the losses are usually given in a tables are in so many feet of water pressure loss per 100 feet of pipe. The extra loss caused by the fittings and valves are given in terms of equivalent lengths of pipe. For example, a globe valve might have the same loss as, say, 22 feet of pipe. Entrance and exit losses are the additional losses caused when a fluid enters or leaves a pipe. The tables also give an equivalent length of pipe for these losses. Okay, let's look at an example which has all the different factors which we've discussed. Let's say we want to pump 1,500 gallons per minute. First, there is discharge static head, which is 60 feet. The discharge pressure head is 26 psi-G. Okay, first thing, let's convert the 26 psi-G to feet. When we multiply it by 2.31, we get 60 feet of water. We have 140 feet of 8-inch pipe here on the discharge side. From the handbook, we find that an 8-inch pipe handling 1,500 gallons per minute has a loss of 6.32 feet per 100 feet of pipe. So, since we have 140 feet of pipe, we have 6.32 times 140 divided by 100 equals 8.8 feet. We have 3 elbows, and we find in the handbook that an 8-inch L is equal in loss to 20.2 feet of 8-inch pipe. So the loss for the 3 elbows is 3 times 20.2 divided by 100 times 6.32, which gives us 3.8. By the same process, we find that a gate valve loss is 0.3 and a check valve is 3.3. The exit loss, where the pipe enters the tank, again, as taken from the handbook, is 1.4. When we add all these up, we get a total discharge head of 137.9 feet. Okay, now for the suction side. First off, we have a minus 10 feet of suction static head. Since the suction tank is open to atmosphere, we have 0 suction pressure head. So we record these 2 facts. We've got 10 feet of 10-inch pipe. The handbook shows the loss to be 2.1 feet per 100 feet of pipe. So we have 2.1 times 10 over 100 equals a minus 0.2 feet. One 10-inch elbow has a loss of 0.5 feet, and the entrance loss is 0.6. When we add all these up, we find that we have a total suction head of minus 11.3 feet. Our total head then is discharge head less suction head. So we have 137.9 minus a minus 11.3, which gives 137.9 plus 11.3, or a total head that the pump will operate against of 149.2 feet. If we want our answer in PSI, we divide by 2.31 and we get 64.6 PSI. Calculations of the total head for any type system are essentially just the same as this one. Just break the losses down into individual parts and then add them all up, being careful to keep the sign correct. Then you finally subtract the suction from the discharge. Okay, now for another definition. Specific gravity is a term used to compare the weight of a material to an equal volume of water at 4 degrees centigrade. Now let's explain this a bit. If we have 1 pound of cold water in this glass and we find that an equal volume of this red liquid weighs 2 pounds, then we say that this red liquid has a specific gravity of 2. If, on the other hand, we find that the same amount of gasoline weighs 0.75 pounds, we would say that its specific gravity is 0.75, which it is, by the way. Many liquids vary in volume with changes in temperature. Since most pumps are rated in gallons per minute, or GPM, if a process is being used which requires a certain weight of fluid to be delivered, then the difference in specific gravity, due to temperature changes, will have to be taken into account. To determine the volume at the hot condition, we use this formula, where hot GPM equals cold GPM times cold specific gravity, divided by the hot specific gravity. Here's an important statement which has to do with specific gravity. It's worth remembering. A centrifugal pump with a given impeller, speed and size, will develop the same head in feet, no matter what the liquid or its specific gravity. Now obviously this rule doesn't apply to high viscosity materials like coal molasses. To illustrate this rule, let's look at a sketch. Here let's imagine that the black balls are water and that the white balls are gasoline. Since they both leave the impeller traveling at the same velocity or speed, they will both be thrown to the same height. If the balls leave the impeller and travel in a horizontal direction, they'll both be thrown the same distance. But now, if we put our toy auto in front of them, the greater pressure will be exerted by the black balls, since they weigh more. That is, they have a higher specific gravity. Therefore, we can see that we develop a higher discharge pressure with the water pump, although both are pumped to the same height in feet. Hydraulic horsepower is the work required to change a liquid from one elevation, pressure, and velocity to some other elevation, pressure, and velocity in a given time. This formula will determine the hydraulic horsepower for any liquid. It is hydraulic horsepower equals GPM times total head times specific gravity divided by 3,960. Brake horsepower is the actual horsepower required at the pump shaft to drive it. Brake horsepower includes all the losses in the pump itself. These include losses due to friction and turbulence of the liquid in the pump and friction of the packing and bearings. The ratio of the difference between the delivered horsepower and the input brake horsepower gives us the efficiency of the pump. Okay, now back to our original statement. A centrifugal pump with a given impeller, speed and size, will develop the same head in feet no matter what the liquid or specific gravity. This means that even though most all pump performance curves are figured using cold water, that if you're handling a liquid at a different specific gravity, you can still read capacity in GPM, the total head in feet of liquid, and the efficiency directly off the curve without any adjustment. Brake horsepower will, however, have to be multiplied by specific gravity of the liquid being handled. Okay, now let's look at a regular pump curve. It should be noted that there is a separate pump curve worked up for each particular pump design, and that no two pump curves are exactly alike. All right, along the bottom we have GPM, and up this side, total head and feet. Say we want to pump 325 gallons per minute, and we calculate our total head to be 44 feet. We would enter the curve right here at 325 and go up until we cross the 44 feet horizontal line, which shows us that this pump, with a 7 3/4 inch diameter impeller and a 5 horsepower motor, will do the job. The efficiency would be approximately 78%. Now you will notice that there are several different diameter impellers plotted on this same curve, which brings up another point. We can change the performance of a given pump by changing the speed at the periphery or edge of the impeller. This can be done in one of two ways: change the impeller diameter or change the RPM. First, let's look at changing the diameter of the impeller. The impeller for a given pump is cast a certain maximum size, and then for any diameter less than that, we simply set it up in a metal cutting lathe and machine it down to the desired diameter. There are, of course, limitations to how large and how small you can go, but if you stay within the limits as shown by the manufacturer's curves, you'll be okay. As you can see from the curve, the smaller impeller diameters require less horsepower. Normally, when a different impeller diameter is required, we can extrapolate directly from the curve, which means we pick it off between the plotted points. Okay, back to our pump selection. Since right here is the point at which we want to operate, and it's midway between the 7 3/4 and 7, we can see a curve approximately halfway between would be for an impeller 7 3/8 inches in diameter. So we just draw it right in, and we find that a 7 3/8 impeller would produce exactly our requirement of 325 gallons per minute at 44 feet head. In this case, trimming the impeller down to 7 3/8 has an additional advantage. Let's assume that we had left the impeller at 7 3/4 inches. As long as the speed is constant, the output from a pump will always fall at some point on the curve for that particular impeller diameter. Now, instead of producing the 44 feet head, which we require, the head developed by the pump will be somewhere along this curve. And since there is more head than 44 feet here, there will be more flow than calculated because more pressure will shove more water through the pipes. So we will actually be operating at some point along here. Now notice we are above the 5 horsepower curve, and therefore the motor will be overloaded. Above the horsepower curve means overload. Anywhere below it is okay. I should remind you of something right here. While you may get away with continuously overloading an open drip-proof motor, 5 or 10%, if you put a totally enclosed or explosion-proof motor of the same horsepower in an overload condition, you'll burn it up for sure. This is true because there's no overload safety factor designed into totally enclosed and explosion-proof motors. A common mistake is for a mechanic to see an application where the motor is heating up and say to himself, the pressure is too much. So he opens up a valve which allows more flow, moves us out here on the curve, and then he really does burn the motor up. Remember, in the normal operating range of most impeller designs, increased flow usually means increased horsepower. If you want to calculate what a change in impeller diameter will do to the performance of a pump, here are the rules. A, the flow in GPM will vary directly as the diameter. That is, cut the diameter 10% and you'll cut the flow 10%. B, the head varies directly as the square of the diameter, which means that double the diameter and the head is 4 times as much. C, the horsepower required varies as the cube of the impeller diameter. For example, if we double the impeller diameter, we will require 8 times the horsepower. D, the efficiency remains the same for small changes. The other way to change the speed of the edge of the impeller is by changing the speed of rotation of the impeller. Here, as was the case with a change in impeller diameter, A, flow changes directly as the speed. B, head varies directly as the square of the speed. And C, power varies as the cube of the speed. D, efficiencies are unchanged for for small changes in speed. Okay, for one final explanation, net positive suction head. This term is usually misunderstood by purchasers of centrifugal pumps. Net positive suction head, or NPSH, is the absolute pressure above the vapor pressure of a liquid being pumped, measured at the pump suction flange on a gauge at the pump center line. The suction side of a pump doesn't actually suck up anything. What happens is like when you drink a soft drink through a straw. A partial vacuum is created, and atmospheric pressure forces the drink up the straw. Okay, what does that mean? Well, with cold water at sea level, we start off with atmospheric pressure, which is 34 feet, and deduct all the losses along the way until we get to the pump flange, and what's left is the net positive suction head. There must then be enough of the atmospheric pressure left when the liquid gets to the pump flange to force the liquid into the pump. Each manufacturer calculates the minimum NPSH required to move the liquid into each pump under varying flow conditions, and usually puts it right on the pump curve. For example, our pump at 325 gallons per minute would require an NPSH of about 9 feet. When calculating NPSH, differences in vapor pressures must also be considered. For example, Cameron's handbook shows water at 150 degrees has a vapor pressure of 3.7 psi, which is 8.5 feet. So if we're pumping 150 degree water, when we get to the pump flange, we must subtract an additional 3.7 psi, or 8.5 feet of water from the gauge reading to determine how much is left to force fluid into the pump. Also, at higher elevations, say like in Denver, there's less atmospheric pressure because less air is piled up above us. There, we would start off with only 24.5 feet available pressure instead of 34. If you're having problems with noise or erratic operations, then it's quite possible you don't have sufficient net positive suction head. You can determine what your NPSH is by installing a vacuum gauge at the pump suction flange and subtracting the gauge reading from atmospheric pressure, after taking into account any differences in elevation or vapor pressure. This ends part 2 of centrifugal pumps.